Howdy, today in Flippin Science we're looking at the physical properties of organic compounds. So science understanding we're going to cover. Physical properties of organic compounds are influenced by molar masses of the molecules and by the number and polarity of functional groups. So predict, explain and compare the melting points, boiling points, and solubilities in water and in non-polar solvents of organic compounds given their structural formulae. So we're looking at physical properties, specifically melting, boiling points and degree of solubility in water. We're really going to focus mainly on boiling point and solubility. So all three of these factors are affected by how long the carbon chain is and also what functional groups are present in the organic compound. A group like an amine group here, that will increase solubility in a compound because you can make hydrogen bonds between the amine and water molecules. An alcohol group present on a really long carbon chain, however, that's not going to really affect the solubility that much. So that's what we're going to look at today. We're going to look at how carbon chain length and functional groups affect boiling point and solubility. So to start with, we're going to look at the effect of chain length. So we're going to use the same functional group, and all we're doing is we're adding carbons, and we're going to have a look at the effect that has on melting and boiling point. So let's start by having a look at the alcohols. So here we can see we're just adding one carbon on as we go down. So we've got 1, 2, 3, 4 carbons in our chain. And if we have a look at the effect of the boiling point, as we increase the number of carbons in the chain, the boiling point also increases. The effect is clearer on boiling point than it is on melting point, so there's a bit of a mess in the data here. It's all real data. That doesn't mean it's not true, it's just it doesn't really follow the pattern as well as the boiling point does, and that's probably why we're going to focus on boiling point a bit more today. And the reason for this is, as we're increasing the number of carbons, we're going to increase the strength of dispersion forces acting between the molecules. So the longer the carbon chain, the more atoms you have. The more atoms, the higher the molar mass. But really you're adding in more electrons. The more electrons you have, the stronger the temporary dipoles produced when the electrons pull at one end of the molecule or the other end of the molecule and produce a temporary dipole. So the longer the carbon chain, the stronger those dispersion forces, the higher the boiling point. Now we're going to have a look at how alcohols compare to aldehydes and ketones of a similar molar mass. And what happens is you'll see the alcohols will always have a higher boiling point compared to a similar aldehyde or ketone based on the molar mass. And the reason for that is the hydroxyl group that's present in alcohol. So if you look at ethanol down here, we've got the hydroxyl group, the OH group. It's a really polar group. And in fact, it will make hydrogen bonds between other molecules of the same substance here. So the oxygen is quite electronegative, the hydrogen is not very electronegative at all. So the electrons in this bond are hovering around the oxygen. That's almost exposing the proton that's the middle of the hydrogen atom. What that means is this is a very polar group, and that's how we get hydrogen bonding. So the alcohols can hydrogen bond with each other, and that requires a lot more energy to put in to break those molecules apart than if this hydrogen bonding wasn't present. So let's have a look at the aldehydes and ketones now. So aldehydes and ketones do have a polar group. They have the carbonyl group. So there's a delta negative oxygen like we had in the alcohol. But the electronegativity difference between the oxygen and the carbon here isn't as great as the electronegativity difference between the oxygen and the hydrogen. So what that means is this isn't as polar a group, and that means the strength of attraction between these, the dipole that's generated, isn't as strong, which means it's a bit easier to break. You don't have to put in as much energy to break the dipole-dipole bonding between your aldehyde or your ketone. And that has an effect if we have a look at the data. So here we're comparing hexane 1-ol, hexane al, and hexane 2-one. We can see they have a very similar molar mass, but the boiling point of the alcohol is 20 degrees higher, 30 degrees higher, compared to the aldehyde of the ketone. So, although they're all polar, the hydroxyl group in the alcohol is more polar, which means we get stronger secondary interactions, which requires more energy to separate, and therefore a higher boiling point. So let's have a look at some other examples. So here we have propane 1-ol, propanal, propanone. We can see a very similar molar mass, but the boiling point of the alcohol is almost double that of the aldehyde or the ketone. If we have a look, here we're adding a lot more carbons in, so we're up to 10 carbons, so decane 1-ol, decanal, and decane 2-one. Again, the molar mass is similar. The increase in boiling point isn't as significant though, because once we're starting to get this long, the number of carbons in the chain and the dispersion forces acting between the chains is going to have a much greater effect than the simple polarity that's going on with the hydroxyl groups at the end here compared to the aldehyde and ketones carbonyl group. So there's only a 19 degree difference-ish, 20 degree-ish difference between these. Now we're going to talk about solubility. And solubility in water depends on a few things. It's the functional groups that you have present and whether they can make a secondary interaction with water, and also how long the carbon chain is. So a polar group, like an alcohol, so here I've got diols, dicarboxylic acids, and diamines. So if you have a functional group that is polar and can make a secondary bond with water, specifically it would be great if it could make a hydrogen bond, and it's small, it will be soluble. But if we have a look down here, our classic example here is oil and water, and they just don't mix. And the reason for that is, well, we'll have a look in a minute and we'll see why that is. So to be soluble in water, you need to be reasonably small, and you also need to make some kind of secondary interaction with water. So let's have a look at an example in terms of solubility for a homologous series. In this case, it's aldehydes. So let's have a look at how soluble they are in water and what happens when we add carbons. So as we go down here, we're adding carbons. So 1, 2, 3, 4, 5, and then we've got 8. So we're making a bit of a gap down here. Methanol is completely soluble in water. You can put as much methanol in water as you like, and it will completely dissolve. Then as we add an extra carbon, we're reducing our solubility from basically miscibility, to only 16 grams per 100 grams of water. And then if we add another carbon, we're halving that again. As we're adding more and more carbons, we're adding less and less soluble until at 8 carbons, the aldehydes are just not soluble anymore. So once we have, say, 8, 9, 10 carbons, they just won't dissolve in water, and you'll get that extra layer forming, like we saw with the oil and water before. And this is the pattern that you'll see in your organic compounds. If you have a polar group, so an aldehyde does have a polar group, but as you add carbons, you're reducing its solubility. So the longer the carbon chain, the less soluble it is. So all this comes down to water. Water is a very small molecule, and it also can hydrogen bond with itself. So different water molecules can hydrogen bond with each other. So to be soluble, you need to be small enough to sit in between those water molecules, but also make some kind of secondary interaction with those water molecules. And if you can't do that, you won't be soluble in water. So here we have an alcohol. This is ethanol. So we've got a very polar hydroxyl group that can make hydrogen bonds with water molecules. So it's small. It has a functional group that can make a secondary interaction with water. In this case, it's a very strong secondary interaction. It's a hydrogen bond, so that will make it very soluble in water. Over here we have a triglyceride. So this is like an oil or a fat, like we had in that picture before. We had oil not mixing with the water. It has this several really long non-polar carbon chains. It does have a bit of polarity at the top, but the polarity at the top doesn't overcome the lack of polarity in the carbon chains present here. Water molecules won't be able to make much of a secondary interaction with these non-polar carbon chains. So because of that, it just doesn't dissolve with water. It can't sit between the water molecules, and it's not making a secondary bond with water molecules. So when you're looking for solubility, you're going to be comparing normally one compound with another. You're looking at length of carbon chain and the number of functional groups that can make a secondary interaction with water. So that's what you're going to look for. So let's have a look at nonpolar compounds now. Now, nonpolar compounds are going to be soluble in other nonpolar compounds for similar reasons. You're going to get similar levels of attraction between the nonpolar substances, and that leads them to being soluble in each other. Now, rather than having strong secondary interactions like hydrogen bonding, the dispersion forces are the secondary interactions that are causing the attraction between the molecules. So what this leads to is a rule called like dissolves like. What that means is if you have a nonpolar compound, it will be soluble in a nonpolar solvent, and if you have a nonpolar polar compound, it will be soluble in a polar solvent. So don't repeat it back to me, because even though it is an adage, you're not explaining anything just by stating like dissolves like. So the reason why you need to explain it is you need to talk about the interactions between the molecules. Let's have a look at an example of this. So an application of this is vitamins in your body. There's two types of vitamins, water-soluble and fat-soluble. To give you an idea of the structure of a fat, here's a triglyceride down here, so you can see it's reasonably nonpolar. So my question is, out of vitamin C and vitamin A, which one is going to be fat-soluble? So if we look at vitamin C, we can see it's got a reasonably long carbon chain. We've got 1, 2, 3, 4, 5, 6 carbons in the chain. But if we have a look, we've got a polar hydroxyl group, polar hydroxyl group, 1, 2, another 2 polar hydroxyl groups, and some other polar groups in here as well. So that means that there's a lot of polarity here, and that makes vitamin C very polar. So that's water soluble, because water is polar too. You get hydrogen bonding between the hydroxyl groups at least, as long as the other interactions are between the other groups over here. So what that means is if you take in too much vitamin C in your body, you just urinate out the excess. It passes through your body and as a waste product, because you don't need as much. You don't need over what you're using. If we look at vitamin A, however, we can see it's got a reasonably long non-polar chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So lots and lots of carbons in a long chain. We've got some alkene groups in here, so we've got some double bonds as well, so they act to straighten it out. We do have a polar hydroxyl group. That's one polar hydroxyl group for a really long chain. What that means is you'll get a lot of secondary interactions between vitamin A and a triglyceride, like we have down here, since this is has a long carbon chain as well, so there'll be strong dispersion forces acting between these and they will be attracted to each other. What that means for vitamin A is you don't need much vitamin A, it just gets stored in your body fat. A small little ampule of vitamin A will last you about 1.5 years. So you don't need too much vitamin A, it stores in your body's fat and you don't urinate it out as a waste. So here's an old exam question. So here we have amphetamine. Amphetamine has low solubility in water and is usually taken in the form of salt. Using the structural formula above, explain why amphetamine has a low solubility. Now, the key is it's low solubility, not insoluble. And the other key is this is for 2 marks, so we need to have 2 ideas that we're talking about here. If we have a look at the structure for the amphetamine, we can see there is an amino group here, an NH2 group, an amine group. What that means is this is quite polar. Nitrogen, hydrogen, oxygen, hydrogen, fluorine, any of those bonds, they can make hydrogen bonds with water. So this group will be able to make hydrogen bonds with water, and that will lead to some level of solubility. But we have a really long carbon chain here. Here we have a benzene ring. So this aspect of it won't be particularly soluble in water, particularly the benzene ring. They're not very soluble in water at all. So the reason why it has a low solubility, it does have some aspect of solubility due to the amino group here that can form hydrogen bonds with water, but the presence of a long carbon chain will reduce its ability to dissolve in water to a level where it would be mostly insoluble, I would suggest. So today on Flipping Science, we looked at the physical properties of organic compounds. That's it for Flipping Science today. See ya.